So hi guys, so we are back with another video that is we're going to discuss questions from Newton's laws of motion, right? So in mechanics, we're going to discuss questions from Newton's laws of motion, right? So in M13 tube, right? So in M13 tube, we're going to discuss the ninth question, right? So let us see what it is, all right? So it says following graph shows the VT curve of a vehicle of mass 500 kilograms. Plot the variation of force with time. We need to draw a curve, uh, force against the time. What they have given is velocity against time, right? So yeah, so how do we convert a velocity time graph into a force time graph? So what procedure do we will have to follow? What do you think? Simply what we need to do is, guys, right? So simply we can like, for example, we know the equation. If we consider F equals ma, right? So like the mass is going to be constant, right? The mass is a constant. So according to Newton's second law, if we consider the equation F equals ma, mass is a constant. In that case, we can write force is directly proportional to the acceleration, right? So instead of in that case, instead of drawing a force time curve, we can draw first of all an acceleration time curve, and that acceleration time curve will be equal to the force time curve, right? So will be equal to means will be proportional to the force time curve. Why? Because the acceleration is directly proportional to the force, right? So right, fine, let us draw the force time curve, right? So if we draw the force time curve in this itself, right? Sorry, not the force time curve, the acceleration time curve, right? So in 10 minutes, within 10 seconds, the object is having a for 10 seconds, the object is having a uniform velocity, not a uniform velocity, a uniform increase of velocity. So this is what? This is a, in a VT graph, if it has a uniform graph, like actually from a VT graph, the gradient gives what? In a VT graph, the gradient gives the acceleration, isn't it? It gives the acceleration. So we need to check the gradient. Here, the gradient is plus, isn't it? It's a plus value, right? So it has a constant gradient as well, which means if we draw the AT curve, it has a constant acceleration, because the gradient is, since the gradient is constant, the acceleration is constant. Okay, next what? Next, if you see, the velocity is constant from 10 to the 20th second. From the 10th second until 20th second, the velocity is constant. If the velocity is constant, what can you say? Simply the gradient here is zero. The gradient here is zero. Therefore, the acceleration will also be zero. So the acceleration will be zero. And then what about this gradient? If you see this gradient, it's a what? Okay, this is a positive. Opposite side is positive. Adjacent side is negative, because it's 20 minus 25. 20 minus 25 means a negative value. So if you get the gradient, opposite over adjacent is negative. So plus or minus is minus. So therefore the gradient is going to be from 20th second to 25th second, right? The gradient is negative, which means the acceleration is a negative acceleration, right? Somewhere like this, right? Okay. And then what about this? So if you see this gradient, it is having a negative, opposite side is negative, adjacent side is plus 30 minus 24, 25, plus 30 minus 25, which means this is plus. So negative over positive, like, you know, right? Gradient is tan theta. Tan theta is opposite over adjacent, right? So if you see the opposite is negative value, actually 20 minus 20, opposite is negative, adjacent is positive. So which means it's also a negative gradient. But if you see the gradient, it's going to be quite, the gradient is quite less, right? So therefore, let us mark it somewhere in this way. All right. Okay. So what else? And then once again, Once again, the acceleration from the 30th to 50th second, the acceleration is so 0. Why? Because it has a uniform velocity from 30th to 50th second. It has a uniform velocity. If it has a uniform velocity, it has a 0 acceleration. And then what about this curve, this part? It has a negative value. This is negative. This is also negative, right? 50 minus this value, 50 minus this value. So it is a positive acceleration. It's a positive acceleration, right? So, and also, what about this part? This also has a positive acceleration, positive gradient. Positive. This is also positive, which means it is, and also it has the same gradient. Same gradient, which means, so this is how the graph is going to look like, right? The AT graph at this, okay, positive gradient, here 0 grade acceleration, negative acceleration, 0 acceleration, and then positive acceleration, right? So these are the time periods: 10 seconds, 20 seconds, 25 seconds, 30, 50, and 60, right? So now you know the acceleration is directly proportional to the force diagram. Force acceleration is directly proportional to force. So instead of using the acceleration here, you can use the force term, right? Actually, you can, instead of the acceleration, you can replace the acceleration as the force axis, right? Because it's proportional. Whatever happens to the acceleration, it happens to the force as well. In the same way, if acceleration increases, force increases. If acceleration is constant, force constant. Likewise. So therefore, instead of the acceleration, you can represent it as the force, right? So guys, try to understand from this question. What you need to understand is from the equation F equals ma, according to Newton's law, since this mass term is constant, you can say the acceleration is directly proportional to the force. So therefore, whenever they ask you a force time graph, so make sure to draw a acceleration time graph first. Draw an acceleration versus time graph, and then that is going to be very similar to the force versus time graph, right? This is how this problem easily can be solved. So here what you need to worry about only, like when drawing the acceleration time graph, is the gradient of the VT graph gives the acceleration. So here the gradient positive, acceleration positive, gradient 0, acceleration 0, gradient negative, acceleration negative, gradient negative, acceleration negative, gradient 0, acceleration 0, gradient positive, acceleration positive, gradient positive, acceleration positive. Pretty simple, right? So it's not a very difficult example. Okay, fine. All right, so let us move on to the next problem, right? Let us discuss the 11th question, right? If you see the 11th question, this is also from M12, right? So this is also from M13, right? So if you see the 11th question, it says find the acceleration of the masses, okay, 8 kilograms and 2 kilograms, and the tension of the string. So first of all, guys, whenever you are given with this kind of a problem, right, so what you need to do is you have to first of all mark all the possible forces acting on the system, right? So actually we know the first force that we are going to mark is the weight, right? It's going to act, the weight is going to act down, mg. If the mass is 2 kilograms, the mass multiplied by the gravitation acceleration, that is going to be the weight, right? So 2 into 10, 20 newtons, right? 20 newton is acting down. So, and then also the tension, T. So tension, T, mutual forces, right? Make sure, okay, T, mutual forces, right? The tension, because since it is the same string, right? Since it is the same string, throughout the string, the tension is the same, right? And then also this guy is going to have a weight acting downwards, 80 newton. And since there's a contact surface, there's going to be a reaction as well. But I think it's not going to be useful for us, but let's see, right? So now let us mark the acceleration as well. Next, after marking all the possible forces in a pulley system, you need to check, okay, when you release this, in which direction is it going to move? So if you see this 2 kilograms, it's hanging, right? It's vertically hanging. So when you release it, it's definitely going to move down with a acceleration. So since this object, 2 kilograms object, is connected with a string to the 8 kilogram object, right? So when this guy moves down with an a acceleration, definitely this 8 kilogram will also move in the forward direction with the same acceleration, isn't it? because it's connected, right? If it goes x distance down, this should also move x distance front. So pretty much the acceleration is the same, right? Okay, fine. So since all these things are marked, next what you have to do is you have to consider the masses. Okay, 2 kilogram, I will consider the 2 kilogram object, and I will apply F equals ma for the 2 kilogram object downwards, right? So what is the force downwards acting on the 2 kilogram? Okay, 20 Newton is acting downwards, and then a force, tension force, is acting upwards on the, like whenever you apply it, make sure to mark the boundary. Okay, so 2 kilograms is this. So what are the forces going out of this boundary? One is going out as downwards 20, another one is going out upwards. So upwards, like we are applying the equation downwards, so the downward forces are considered as positive and the upward forces are considered as negative, right? So like minus t, what's its mass? 2 kilogram. What is its acceleration? A. This is the first equation. And then also for the second object, that is 8 kilogram object, you can apply F equals ma in the horizontal direction. Horizontally, if you apply, now once again, if you are not quite sure about the forces acting on the 8 kilograms, you better mark a boundary as this. So if you mark a boundary, what are the forces going out of the object horizontally? You are applying the equation horizontally, so you check only the forces that is going out horizontally. Okay, tension is going out, right? Tension is going in the same direction where I marked the force. If you see the reaction, this reaction and the weight are going to be perpendicular forces to the horizontal force, like to the direction that I considered. This reaction and weight are going to be perpendicular. So you know, if you resolve a perpendicular force, if you resolve this force towards this side, it's going to be, if it is r, this is going to be, the force acting in this side is r cos 90. So this is going to be 0. So therefore, like, you do not have to worry about the forces which is acting perpendicular to the direction where you apply the equation, right? So you are applying the equation in the horizontal direction. R and 80 are perpendicular forces. So you do not have to worry about these things in that case. So now what are the forces only in the horizontal direction? T is the only force. What is its mass? 8 kilograms. What is its acceleration? A. So this is the second equation. So what you can do is you can add the first equation to the second equation. In that case, what happens is 20 minus t plus t, 2a plus 8a. This minus t to plus t cancels out. So 20 is equal to 10a. A is equal to 2 meters per square second. So now we have found the acceleration of the system, right? So in that case, we can find the tension as well. So since we have found the acceleration, we can easily find the tension as well. That is by equating the, in the second equation, that is T is equal to 8 into A, 8 into 2, right? So 8 into 2. So that is going to be 16 newtons, right? So the tension is going to be 16 newtons, right? So that's pretty much it for the 11th one, right? So yes, let's move on. Right. So guys, we're gonna so what I thought of, like, was since, like, we need to be somewhat familiar with the Newton's third law. So therefore, like, in this question, we are going to see how we could draw the free body diagram of this object, which means, like, based on the action reaction forces and all, how we can draw the free body diagram of this object, right? Okay, so first of all, guys, we need to see okay, how many objects are there? Okay, there is this object and then this object. So these are two separate objects. So therefore, let us mark the weights of those objects, right? So the objects, the weights of them are going to be acting from the center, somewhere from the center, right? Somewhere here, right? Okay, M1G, for example, right? Okay, so the mass of this object is going to be somewhere in the symmetric line. So these things, of course, you might not exactly know, because we have not yet covered the center of gravity part, so no worries. So M2G. So what else? Now what? So let's check the reactions. Now there's two contact surfaces. Let's consider this contact surface. So from this contact surface, a reaction force is going to act on the rod from the from this container, right? So that is going to be, so this is a curved surface. So whenever we deal with curved surfaces, we know when we draw reaction forces, we need to draw a tangent to this curve, right? And we need to draw force, reaction force, perpendicular to it. So the reaction on this figure is going to be perpendicular to that, right? Okay, it's going to be in this way. So if we see this point, this is another contact point. So let us draw the tangent to this point, right? And draw the reaction. So one special thing is these reaction forces will always go through the center, right? Because like if you draw a tangent, right? If you draw a tangent, simply if you draw a tangent, right? If you draw a tangent, so and if you draw a 90 degrees, that 90 degrees always goes through the center, right? If you draw a tangent and if you draw a line perpendicular to it, it goes through the center, the radius, right? So therefore these reactions always necessarily goes through the center, right? So let us remember that as well. All right. And then therefore reaction of this is going to go in this way, is perpendicular to it. So now I guess all the forces are marked, right? So this figure is, I guess, done. All right. So let us go for the next figure in that case, right? So we have to deal with this figure. So here there's three figures, right? So from the three figures, there's going to be weight M1G, M2G, M3G, right? Let us not mark the weight of this guy. Let's not mark the force of weight of this guy. Let us mark only the reactions, right? So there's a contact surface. So if you consider this object, so the surface for that is this. So therefore we need to draw a tangent to this surface and we need to mark the force perpendicular to it, R1. So the other is also R1, action reaction, right? So this is action reaction, one single contact point. So here there is another contact point, which means what you need to do is you need to draw a perpendicular line, sorry, not a perpendicular, tangent line, and then mark the force that goes through the center, right? So it goes through the center, but both these goes through the center, R2. This is R2. So here similarly R3, R3, here R4, R4, right? So pretty much this is the figure. So if we consider this, right, once again, like simply you will see that there's three objects, right? So in these three objects, of course, like this is one object, another object, another object, right? So like obviously from all these objects, there's going to be weight acting downwards, M1G, M2G, M3G, right? So there is a contact surface here. So a reaction force R1, a reaction force R2 perpendicular to these surfaces, right? Contact surface R2, R2, right? So if it is placed on the ground, obviously from here also there's going to be a reaction force R3, R4, right? So simply this is in order to be familiar with action reactions or else the Newton's third law, right? So I guess that's pretty much simple. So let's go for some complicated questions. All right. So yes, right. Okay, guys. Let us see this problem, right? So here, what they're saying is, find the reaction between each of the block in the following, right? So find the reaction between each of the blocks in the following, right? So the reaction, we need to find the reactions, the value of the reaction, right? So they have asked us to assume all the surface are smooth, right? So we need to find the value of the reaction. Okay. So let us draw a free body diagram of this image first of all, right? Let us draw a free body diagram of this image first of all, right? That will be easy, right? So if you consider, it's kind of a situation, right? So initially, like it's going to be, yeah. Sorry, let us draw it properly. Contactless, right? So there's another object as well, right? So let us mark the forces of them acting on them. So there is a contact surface at this point, which means a reaction is going to be there perpendicular to the surface R1, right? And then another reaction force is going to be there on this guy, that is R2, right? So the weight of this guy is going to act vertically downwards, right? The weight mg, the weight of this guy is going to act vertically downwards, simple mg, right? But you can represent those weights as the components, you know, right? Mg sine 30. How did I get that? So, you know, here it is 30 degrees. In that case, this is also 30 degrees, right? So it's geometry. So when you resolve it away from the angle, like, you know, you're going to get mg sine 30. This is going to be mg cos 30. So when you represent it in mg sine 30 and mg cos 30, you do not have to now further worry about the weight, right? So you can erase the weight term, right? Now similarly, let us mark that for this guy also. This is mg simple mg, right? Simple mg cos 30. So in this direction, simple mg sine 30. All right. Okay. So what else? There is another contact surface between these two guys, right? So this is R3 and this is R3, right? Contact surface. Since there's a contact surface here, like simply there's going to be a reaction force acting between them, right? So initially, what we need to do is, guys, we need to apply by considering the complete object system, by considering the like, okay, we couldn't mark the upward force capital F, right? We couldn't mark the upward force capital F, right? By considering the complete object, what we can do is, by considering the complete system, right? So what we could do is, we could apply, by considering the system, we could apply in the upward direction F equals ma. What is the upward force? So what is the upward force? Capital F, right? The upward force is, in that case, capital F. Is there any other upward forces? This R to this R cancels out, because when we consider the system, these two forces will get cancelled out, right? Because they are internal forces when you consider the system completely. And these forces, the reaction mg cos 30, R2 mg simple mg cos 30, all are perpendicular to the plane. It's perpendicular to the direction that I apply F equals ma, right? So therefore, they are not going to come into the equation. So capital F is going to come into the equation. So I'm going to apply the equation in the upward direction. So can you see there's two forces acting down the plane? Mg, simple mg sine 30 and capital mg sine 30. So therefore, we need to subtract capital mg sine 30 and simple mg sine 30 as well. So what is the total mass of the system now? Capital M plus simple M. Let us assume both, like obviously let us assume due to the application of force capital F, these guys are moving up with an acceleration a, it seems, which due to the application of force capital F. Let us assume these guys are, the complete system is moving up the plane with an acceleration a. So we are going to find that acceleration, simple a, right? So for that, what we're going to do is, okay, F minus sine 30, g sine 30, capital M minus capital M plus simple M, capital M plus simple M a. So the acceleration, if you simplify, F over capital M plus simple M minus g sine 30. Sine 30 is half, g over 2. This is going to be the acceleration if you simplify, right? This is going to be the acceleration of the objects, right? So now what do we need is not the acceleration of the system. What we need is not the acceleration of the system, but what we need is the reaction acting on the between the objects, the reaction acting between the objects, right? We need to find R3. So to find R3, what I'm going to do is, I'm going to apply, I'm going to consider only the only the simple lem object. I'm going to consider only the simple lem object. I'm going to consider only simple lem object and apply if equals ma in the upward direction. I'm going to consider only simple lem, right? So what is the upward force? The upward force acting on the simple lem object is R3, and also its weight is acting downwards, isn't it? Its weight is acting downwards, if you see, right? Its weight is acting downwards. So if I apply F equals ma to simple m object, if I apply F equals ma, right? F equals ma, what is the upward force? R3, sorry, the upward force is simply R3, right? So R3 minus its weight is acting downwards the plane, mg sine 30, right? So R3 is acting upwards, simple mg sine 30 is acting downwards. That is the only two forces which is acting along the plane. The other forces, the R and mg cos 30 are what? They are perpendicular forces, right? So in that case, we can't, we did not have to worry about that. So the mass of the simple M object is simple A, its acceleration is A. So R3 is mg sine 30 plus ma. So R3 is equal to mg sine 30 is half m over 2. M acceleration is what? Acceleration I have already found, that is f capital M plus simple m minus g over 2. So if you see, and if you further simplify R3, mg over 2 plus mf m plus simple m minus mg over 2, this cancels. R3 is going to be given as m capital F capital M plus simple m. So this will be the answer for the reaction between the two objects, right? Okay. So yeah, let us discuss this question as well, guys. So it says two mass 2 kilogram and 6 kilogram attached by a massless inelastic cord. It's attached by a massless inelastic cord passing over a frictionless pulley. The pulley is suspended from a rigid support. Find the acceleration of the system and tension of the cord after releasing the system. So when the system is released from rest, what is the acceleration of the system and the tension acting on the system? We need to first of all mark all the possible forces on this figure, guys, right? So this is 20 newtons, 60 newtons. So the tension T, sorry, tension T, tension T. So obviously we know it's going to go down and this is going to go up, right? So 6 kilogram has a higher weight, which means it will move down. 2 kilograms has a lesser weight, which means it will move up. So now for 6 kilogram, let us apply downwards F equals ma, right? So in that case, we will see, so the downward force acting on 6 kilogram object is what? 60 newtons. So what is the upward force acting on the 6 kilogram object? It is minus T. What is the mass of the 6 kilogram object? 6. What is the acceleration? Okay, this is the first equation. And then for the 2 kilogram object, we are going to apply F equals ma in the upward direction. So what is the upward force? The upward force is capital T. The downward force is minus 20. What is its mass? 2 kilogram. What is its acceleration? A. So this is the second equation. So if you see, guys, if we add the first equation and the second equation, we are going to get 60 minus t plus t minus 20, 6a plus 2a. Minus t to plus t cancels out. 4t is equal to 8a. A is equal to 5 meter per square second. So the acceleration of the system is going to be 5 meter per square second. So let us apply the equation for, but we need to find the tension as well, right? So therefore, let's consider the second equation and apply tension equation for it. T minus 20, 2 into what is the acceleration? 5. So T is equal to 20 plus 10, that is 30 Newton, right? So okay, guys, like we will be back with another video, that is Newton's laws, tutorial session 2, right? So make sure to cover that as well, right? So yes, thank you, guys. See you on the next session, right?